Hello everyone, welcome to the technical session number 6 of SVR. So we will have 6 papers in this session. My name is Liliane Machado and I will be the chair of this session. So we will have 6 papers. After each video, we will have some time for questions. So please use the chat area to make your questions. And at the end, if we have some time, we can reopen for questions. So welcome again, and let's go for the first paper. The first paper will be presented by Vitor Gouveia de Menezes Lira from UFPE. Please, Vitor.
Hello, my name is Victor, and today I'm going to present the paper, Development of an Efficient 3D Reconstruction Solution from Permissive Open Source Code. In the past years, the interest in virtual environments has constantly increased as a form of keeping data of historical objects for museums or even helping designers to modulate real-world scenes. Nowadays, that intensified, with even classes and conferences in virtual environments. All these examples could be greatly improved by making 3D reconstruction of real-world objects and scenarios. The motivation behind this work was to create a photogrammetry application which consists of taking images of an object or ambient as input and making a 3D model of the subject. We wanted to create this application using only permissive license solutions, so it can be used commercially, and with an emphasis on faster processing, given that most photogrammetry applications have a high processing cost. To make our application, we composed different methods. One of them was the COM abstraction for motion, which takes the images as input and output an estimation of the camera poses and a sparse point cloud reconstruction. Originally, it has some non-permissive dependencies, such as SIFT and the free image library. So, we used the modified version, which has the dependencies changed to Akazi and OpenCV. Another method used was the RMVSNet, a multi-view stereo deep learning technique that uses convolutional neural networks and gated recurrent units to estimate a depth map for each input image. Because it is a deep learning approach, it can be a lot faster than geometric approaches that other applications use. At last, fusing those depth maps, we end up with a point cloud. And for that, we process it using a permissive point cloud library. It is responsible for filtering, resampling, and estimating normals of our point cloud, and also making a surface reconstruction and mapping the texture to this surface. So, our complete pipeline works as follows. First, it inputs a set of images and makes an estimation of the camera localization using the structure for motion from COMAP. Then, it estimates a depth map for each input images using the RMVSNet. After that, we fuse these maps into a dense point cloud and filter it to decrease the density and remove some outliers. Then, we create a mesh using a Poisson surface reconstruction algorithm. And finally, it maps textures on the mesh, leaving the final reconstructed 3D model. To evaluate our application, we made 2 tests. In the first, we made a quantitative evaluation on one of the sets of images from the D2 dataset using the provided ground truth point cloud. In the second test, we extracted 3 sets with different sizes of 46, 86, and 125 frames from our own Pikachu dataset, mainly to evaluate the execution time. In all these tests, we compared our application with state-of-the-art photogrammetry methods, COMAP and MV. This image shows the reconstructed point cloud mesh and textured mesh of the object from the DTU dataset. Checking the mesh result, it is clear that the MVE is a lot noisier compared to the other methods, which is reflected in the 3D texture object obtained. But it is also possible to notice a loss of details in the proposed pipeline. So using the ground truth point cloud, we calculated the precision, recall, and F-score of the reconstructions, and our pipeline obtained a point cloud with a higher F-score. These results show a clear improvement in the precision of the points, especially when compared to MVE, and it obtained a similar recall to the other methods. Here, we have the textured mesh generated from each subset from our Pikachu dataset. As you can see in the first row, when using only 46 images, our solution has poor reconstruction quality. But when we increased the number of pictures used, the quality had a remarkable improvement, as can be seen in the last row. Our solution was as detailed and complete as CoMaps and better than MVs. So looking at the execution time of each technique, it is easy to note that ours was a lot faster. It had a decrease of approximately 70% on average in time execution compared to both CoMap and MV. In conclusion, our works was able to develop a photogrammetry solution that uses only permissively licensed techniques and also achieve a good cost benefit in terms of quality and execution time compared to other state-of-the-art solutions. Thank you.
So, Victor,
Hello.
I don't see any question, but I have one for you. I read your paper, and I'd like to know which characteristics presented the results you obtained, how they improve or expand some commercial solution. If this is a point.
I'm sorry, can you repeat the last part?
Yes. Uh, how your work can increase or improve some feature of commercial solutions, and if you can also say how do you intend to continue or use your results.
Okay, so if I understood it correctly, you asked how the time improvements would uh, impact the solution being permissive. Is that it? Okay, so um, yeah, it's more of we wanted to make a permissive solution, and because most of photogrammetry applications take a lot of time to reconstruct an object, we wanted also to focus on this, on making it more time efficient, right? And to the second question of what we will continue developing, there's a lot of things we could change. They are not great, as you see, as we told in the paper, especially in regards to texturing the object. There are some flaws still, so we will work on that on the future, and also in the reconstructing the mesh, we can also improve in that.
Okay, thank you, Victor. We have another question, but I will move to the next paper so we can go back at the end. Could be Marcio Pinho that made the question in the chat, so we can return at the end of the section. Thank you, Victor. Let's move to
Okay,
the
thank you.
next paper. The next paper is from the Federal University of Juiz de Fora. Who will present is Gustavo Moura.
Hi, my name is Gustavo Magalhães and I will present VinSLAN, Virtual Environment Modeling through SLAN. Simultaneous localization in mapping is a well-known problem in computer science. With solutions for this problem, we can extract information from the environment and recreate a 3D map with the capability to localize ourselves in it, for example. But we don't know what objects are in this virtual environment. One solution for this problem is to use object detectors. Modern object detectors are based on machine learning, especially deep convolution neural networks, DCNNs. DCNNs identify 2D objects in images according to their training, and its output is a class label and a bound box for each object detected. So we wonder, joining a visual SLAN solution in the DCNN, could we localize the objects in the 3D map? Furthermore, with this map, could we produce a virtual environment analogous to a real indoor environment, with the objects detected in it using only RGB images? To answer these questions, we choose these methods and techniques to compound a solution. OrbSLAN 2, a popular visual SLAN solution capable of real-time processing. YOLOv2, a lightweight DCNN also capable of real-time processing. The works of Rubino et al. Has object pose estimator. The pose estimator is based on the conversion of convex ellipses in different views to a quadric ellipsoid, without considering details of the surface and shape of objects. The original OrbSLAN 2 has 3 threads. VinSLAN adds 2 new threads to the original OrbSLAN 2. A keyframe after optimization by local mapping thread is processing at the object detection thread with the YOLOv2 DCNN to obtain the conics. In the object optimization thread, the conics are grouped using geometric information, and linear and nonlinear optimizations are used in each set to obtain quadrics that represent the objects detected. We add the objects in the full bundle adjustment function to improve the map optimization. The initialization step depends on the parallax between frames, significantly varying the beginning of the camera trajectory estimation between executions. The OrbSLAN 2 scans the environment generating a 3D map. The inputs of YOLOv2 are the keyframes, and the output are the labels and bound boxes of detected objects. The ellipses are associated in objects using geometric features. The ellipsoid of each object is calculated using linear and nonlinear optimizations. At the end of scene, the ellipsoids are fully optimized. The labels of each detected object are queried in a model library. The models are placed according to the object's 3D position in a virtual environment. As expected, the inclusion of 2 new threads in VSLAN and the execution of full bundle adjustment at the end of every new keyframe processing increases the time execution. However, real-time processing was kept due to execution of 2D object detection and 3D object optimization steps in GPU. We evaluate the impact of inclusion of ellipses in full bundle adjustment function using the root mean square error of absolute territory error. We compare the VSLAN results with the original OrbSLAN 2 and OrbSLAN 2BA, a variation which executed the original full bundle adjustment at the same point that VSLAN performs. For sequences with few numbers of frames, less than 2,360. There was no evidence to support the improvement of camera trajectory estimation with the addition of objects in the full bundle adjustment. For sequences with more than 2,503 frames, the difference between the results of Opson 2BA and Visland showed an improvement of camera trajectory estimation with the addition of new elements in the BA. With more frames, the number of keyframes generated increases, and this leads to an increased number of elements in BA calculation, further improving the optimization. Our main contribution with this work is the proposal of a virtual environment modeling method that recognizes relevant objects in an indoor scene using exclusively RGB images with robust odometry. We provide the integration of a 2D object detector, a 2D to 3D object recovery method, and a monocular visual SLAM solution. Thank you for watching. If you have any questions or suggestions, contact us by mail.
Thank you, Gustavo. Gustavo is here. So we need some seconds to see the questions, but we can talk a little bit while we wait. Could you make some comment about how expensive is your solution? Expensive, I mean processing time, considering processing time.
Because the optimization steps, specifically the non-linear optimization step, the cost is high, but in some hardwares with top of line hardwares, the cost is minimum compared to the execution time, all the execution time. So if we have a, a hardware strong enough to process all the steps, as you can see in the presentation, in the paper, the whole Benslan is processing at real-time processing. So the cost execution time is improved by the hardware optimization, hardware strong hardware. Answer the question.
So it's hardware dependent.
Hardware, yeah,
of course.
Of course, because all designing systems is highly dependent of hardware.
Okay, thank you, Gustavo.
Thank you.
I can see any questions, so thank you very much, and we can move to the next presentation.
Thank you.
That will be made by José Gomes from the UFPE. So let's see it.
Hello everyone, my name is José Gomes. I'm part of the research group Voxar Labs. Today I will present the work called Comparison of RGBD Sensors for 3D Reconstruction. The concept of our work is related to 3D reconstruction, which is the process of capturing the shape and appearance of the real object. One way to capture that information is through RGBD sensors. The main objective is to analyze how well 10 RGBD sensors perform when applied to a 3D reconstruction task. The sensors were chosen because they are the most popular sensors in the articles reviewed in the State of Art section. The 10 sensors are Kinective 1, Kinective 2, ASUS Action Pro Live or Backastra Pro, RealSense ZR300, RealSense 435, RealSense R200, RealSense SR300, and RealSense F200. We decided to focus on technology derived from the classification light waves. The comparison between the sensors was performed with the help of the EDU, a robotic arm usually applied for educational purposes. We used the robotic arm at 25% of the maximum speed to make sure that would be slow enough to not interfere in the 3D reconstruction. The recording of the movement made by Do allow us to have a ground truth to the trajectory performed. Now I will explain how the evaluation of the sensor was developed. The first phase was the capture of the environment. Because the coronavirus epidemic, access to the research lab and other common areas has been impaired, limiting the possible environments to be captured. The chosen environment was a child bedroom. The do was placed in the center of the room, which was filled with different objects in different positions and with different textures. Here we can see the captured environment from 4 different points of view. The second phase was the data capture that was divided into 2 phases. Here we have a sample of the data captured by the sensors. The first phase is related to the 3 paths proposed that each sensor must perform through the same movement. The 3 paths can be seen here. They are very similar, but they are notable difference. The first is a simple 360-degree turn. The second is a wave movement, which performs the same movement as the first, but vary the coordinate of the z-axis. The third focuses on changing the distance to objects to assess how it affects the reconstruction. The second phase of the data capture is related to the setup of the real-time map. The capture of the sensor's data was done through the real-time map data recorder module. Unfortunately, some of the sensors, such as Astra Pro, could not have the data recorded via real-time map module available online. To overcome this problem, real-time map was recompiled and support for the device was added. The third phase of the methodology was the comparison of the 3D reconstruction, following 2 analyses, a quantitative one and a qualitative one. The first is a quantitative result. The initial result is about the camera trajectory. Each trajectory saved for each sensor was compared with the ground truth. The error is calculated based on trajectory points sampled every half second. Here we have the total of points saved for each path. Here we have quantitative results about the mean error for all the 3 paths and for each sensor. Now we start to talk about the qualitative results. For path 1, all sensors were capable of performing a full 360 reconstruction except the oldest real sense models, F200, R200, SR300, and ZR300. For path 2, all sensors are capable to perform a 3D reconstruction, except this time no real sense model was able to do it. For path 3, all sensors were capable of performing a full 3D reconstruction, except this time the real sensors models F200 and SR300 and R200. Now we start to talk about the reconstruction analysis. Analyze the results. RealSense R200, SR300 were always among the worst results. One possible reason for that may be the short range of this camera. About the pose analysis. For path 1, Astra Pro, Astra, RealSense D435, Kinect V2, and Action presented a path with a mean error lower than the mean of the error. For path 2, Astra Pro, Kinect V1, and Kinect V2 and Action presented a mean error lower than the mean of the error. For path 3, Astra Pro, Astra, RealSense 435, Kinect V1, RealSense ZR300 performed with more points than the mean. So we have the conclusion of the work. This work performed a comparison of 10 RGBD sensors regarding the ability to generate data for 3D reconstruction application. The worst result pertaining to the RealSense models. Considering the path error for all 3 paths, Astra Pro, Action, Kinect V2, and Kinect V1 were the sensors with the best results in descending order. Both Astra versions and the action, together with the real sensor 435, are a good choice when performing a large-scale reconstruction using mobile platforms. To finish, we made available all data regarding the 10 RGB capture. This comprises over 19.2 gigabytes of data, considering both RGBD and depth stream for all cameras. Thank you for your time.
Thank you, thank you, José Gomes. We have one question from Marcelo Russell. He asked, what do you mean by ground truth?
The ground truth was provided by the IDU robotic arm. He is very precise, and the trajectory ground truth was provided by him.
Okay, can you tell me what's the difference, the main difference between path 1 to path 3? Because I observed that in path 1 you have the lowest mean errors. So can you
Yes,
make any
the,
comments?
the, the path tree is focused on changing the distance between the objects. So the robotic arm uh, takes the sensor more close and more far from the objects, and we try to evaluate how that infers in the 3D reconstruction.
Okay, thank you very much, José.
Thank you
And
also.
we can move for the next paper. So the next paper is from the Federal University of Uberlândia. So let's go.
Hello, I'm Julia from the Assistive Technologies Lab at Federal University of Uberlândia. The goal of this paper was to compare 4 different sensor fusion algorithms for tracking a person's body in virtual reality. We've tested the MPU 9250 Magnetic and Inertial Measurement Unit, or MIMU, sensor from InvenSense. A MIMU contains 3 sensors: an accelerometer, a gyroscope, and a magnetometer that, with the help of a sensor fusion algorithm, can be used to estimate absolute orientation of a body. This can be represented as a quaternion vector or as roll, pitch, and yaw, which are rotations on the x, y, and z axis respectively. The algorithms tested were 1. Accel plus gyro. In the MPU 9250 board, there is a small processor, the DMP. This reads from the accelerometer and gyroscope only and outputs quaternions, so we read them directly from the board. 2. Accel plus meg. For this, we used trigonometry to calculate pitch and roll from the accelerometer. The yaw rotation cannot be obtained with an accelerometer. Thus, we estimated yaw with the magnetometer. 3. Accel plus gyro plus meg. For this, we used the complex algorithms of Mahoney and Madrick, which are further described in their papers. We made 3 types of tests. In the static test, we placed the MIMU board horizontally on a table. Then we measured the time it took until stabilized readings, the signal noise, and drift over time. In the dynamic test, we attached the MIMU to a motor and rotated it back and forth horizontally. We only gathered the yaw readings this time because they're the most prone to errors. In the magnetic interference test, we approached the source of hard and soft iron distortions to the board 1 centimeter every 6 seconds. We then analyzed the resulting data according to certain criteria. The stabilization time shows that the Accel plus Meg is the fastest algorithm, while the Magic is the slowest. In the noise test, Accel plus Meg has the noisiest output, followed by Mahoney and Magic. The DMP had a significant gyro drift over time, so it was excluded from further testing. Moreover, the Accel plus Meg does not have gyro drift, and both Mahoney and Madgwick had very low drift. The result of the dynamic test shows that the Madgwick was the most precise, followed by Mahoney and lastly Excel plus Mag. The magnetic interference was basically the same for all the algorithms. These tests can be better visualized in this VR simulation. Following our criteria, we made a qualitative appreciation. The precision of the algorithms was proportional to their speed. Madgwick was the most precise and the preferred one for our needs. Thank you.
Thank you. Julia is with us. Hello, Julia.
Hello.
Let's wait a little bit for the questions. So, congratulations for your work. It's very
Thank you.
interesting. How do you intend to use these results? Because it seems that the algorithm, the name is Mag. Can you help me? The best one you found, the best algorithm you found, Sorry, the name. Can you help me?
Magic.
Yes. This is the best as you could find. How do you intend to use these results?
Well, can you hear me correctly?
Yes, it's perfect.
Well, I work since 2017. I studied to make a game for post-stroke rehabilitation. So I studied several different stuff about it: 3D modeling, animation, sensors, visual, computer vision. I studied several different topics. And I studied inertial sensing for me to see how it was applicable to the game, if it was uh, what what was the best algorithm, what was the fastest, if this was something that I could implement, the cost. And I ended up studying several different algorithms, and I found out that there's a big difference between them, and the magic was the best one. So I intended to use them to track the arm for the game, basically.
Okay, thank you. We have a question from Marcio Pinho. He's asking, for the dynamic test, could the sensor suffer any interference from the motor?
Uh, it could, but I didn't observe that it could suffer magnetic interference. But uh, I thought about it, but I didn't. I only saw a significant magnetic interference when I approached a big source of hard and soft iron distortion. So the Arduino itself was not capable of distorting the magnetic field enough for me to actually see a difference on the yaw reading.
Okay, thank you, Julia. You continue with us because you have the next two papers. So let's see the next one.
Hello, I'm Julia from Federal University of Uberlândia. The goal of this paper was to optimize and automate 360-degree 3D reconstruction of real objects using photogrammetry, which can be useful in several areas. Among the techniques for 3D reconstruction are 3D scanning and computerized photogrammetry. Both can be really expensive, but the latter can be made significantly cheaper for the same final quality. However, it has a big risk of human errors. These risks can be minimized by automating the photo shoot and controlling the lighting. To do this, professional commercial solutions do exist, but can be expensive. Some alternatives also exist in literature, but can use more than one camera, have expensive lighting solutions, or be complicated to build. For this work, a system was developed to semi-automate the photogrammetry process. It consists of a motorized turntable, a DSLR camera, a tripod, a diffuse light chamber, and a fabric background. The turntable rotates at desired angles and activates the camera automatically. Then, a scratch removes the background from all photos. Finally, the 3D object is reconstructed in any commercially available software. 3 tests were performed. 1. Comparison with manual photoshoot. In this test, the same object was reproduced using manual versus automated photogrammetry. Pictures of the object were taken at a 45-degree inclination, taking a photo every 10 to 15 degrees, resulting in 64 pictures each. As a result, with the proposed method, the model had a better color, was smoother, and more defined. The mesh had an increase of 21% in the vertex number, which indicates better resolution. In the figures, the distortions of the manual process can be seen in red and blue. The time to take each photo was the same, however, the automated process has minimal human labor. Also, the reconstruction time decreased by 58%. This is due to easy background removal. Overall, there was a reduction of 20.3% in total time. 2. Reconstruction of all sides of an object. In this test, a 360-degree reconstruction was attempted by photographing all sides of a rock with the proposed method. A total of 192 photos were taken, rotating the rock 4 times. The reconstruction took 30 minutes and was successful. 3. Impacts of angle between photos in reconstruction time and quality. Lastly, 1 turn of photographs of the rock was tested, varying the angle between photos. It was found that the smaller the angle, the longer the time by a power factor. At some point, it is not worth to reduce the angle anymore. Limitations of the system are the same of photogrammetry in general, which is the difficulty to reproduce.
So here we are again, Julia. Thank you.
Thank you.
You mentioned at the end that you reduced the angle, but how this reduction of angle um, what it result in the size of the model generated? How did you?
As I said, I took two turns of photographs. Then I removed photos. For example, half the photos, one photo every one photo. So one photo I kept, the other I removed. Then I was removing the photos, removed more, then more, then more, and checked the difference in time that it took to reconstruct the model. And I figured out that the time increases in it, sort of a exponential curve, inverse. And while the quality of the model that I estimated by the number of vertex was only a straight line, so at some point it's not worth to decrease the angle anymore. Of course, the decrease of the angle will increase the quality always, but the time will increase exponentially. Very, very. So it would take some time. It would take 9 hours for me to reconstruct. The computer just couldn't handle the reconstruction.
So you could find you could find an ideal angle to do that, yeah?
No, I could. I found out that the 10 to 15 per me It was the best angle because less than that, I couldn't visually see the difference, even though the vertex number increased. Couldn't visually see the difference.
Okay. We have a question from Tiago Silveira. He's asking, does your method cover the base of the object? In other words, can you somehow manipulate the objects so that its bottom is captured by the camera?
Yes, this is a 360-degree reconstruction. All that you have to do is rotate the object and take another turn of photographs. And then you remove the background. When you remove all the background that is behind the object, right, I put a black fabric background behind it. So when you remove that, the software doesn't know uh, what else was in there, the background. I just removed the background. So the software recognizes the photos as a 360-degree object, and he joins everything as uh, a 360-degree model without scenes. Very nice.
Okay, thank you. We have another one. So let's go. Let's see it.
Hello, I'm Julia from Federal University of Uberlândia. The goal of this paper was to compare tracking algorithms for a post-stroke rehabilitation XR game. XR games are video games that are also a form of exercise. For motion tracking, optical devices can be utilized, such as RGB cameras, improving the accessibility of the application. Object tracking is not the same as object detection. The first ones need to gather movement information between frames and thus be lighter. For example, AR markers detection algorithm was too slow for our application, which demands at least 30 frames per second, so that the human eye cannot distinguish between frames. Deep learning approaches were also too slow. With that in mind, object tracking algorithms were searched. The objective is that any holdable or wearable object in the user's home makes them capable of interacting with the XR game. The first option tested was the HSV color threshold algorithm. This tracks the object by masking its color from the background. The other option tested was the 8 tracking API algorithms from the OpenCV library. Among them, the best was the CSRT, discriminative correlation filter with channel and spatial reliability. Besides those, the mean shift and cam shift approaches were also tested. The mean shift was the most promising. At each frame, this algorithm compares the information histograms of parts of the frame with the histogram of the desired object until convergence. Large standardized tests exist for tracking algorithms, but they aren't suited for the color algorithm. Thus, a small dataset was created consisting of 9 videos, each one representing a tracking problem. The object chosen was an AR marker cube because it has a square contour for better visualization. The ground truth was generated using MATLAB. The following evaluations were made. A. Success. A frame was considered a tracking success if the intersection over union ratio between the area of the regions was bigger than 0.5. Then the percentage of successful frames was calculated. B. Precision. The intersection over union value of each frame was calculated, and then the average value of all frames. C. Time per frame. The arithmetic mean of the time to process each frame was calculated. This success chart indicates that both color and CSRT were really good, with CSRT being more consistent and having a higher median. The precision chart indicates that the color algorithm was more precise, but less consistent again. The mean shift was the worst in both tests. The time per frame shows that the CSRT is significantly slower than the others. It was the only one that did not achieve 30 FPS requirements. Overall, the color algorithm won in more tests and was the chosen one for our application. Thank you.
Thank you again, Julia. I would like to know if the precision of the capture, if it can influence the recognition of the movements, because you mentioned that you use it for a post-stroke rehabilitation exercise game. So how it can influence?
Computer vision is a very cheap method of achieving a tracking the arm. It's a very cheap method, it has several advantages, but it's very influenced by lighting. If I change the lighting of the room, if I open a window, I lose the tracking. So it's very influenced by calibrating the color correctly with the lighting, keeping the lighting controlled in a controlled environment without changes in lighting, and then you can achieve a very good tracking, very good, especially if you have a good camera. But it has several influential factors that you have to control.
Can you repeat the last phrase? I couldn't understand.
I said that it is beneficial for being cheaper, and it can achieve very high quality of tracking, very good recognition of the object, but you have to control the environment and the influential factors.
Okay, thank you very much, Julia. I don't know if it's possible to include all the presenters now in the room. Is it possible?
I don't know.
So let's see. Gustavo is there. I don't know if there's someone else, because we have one question for Victor. Is Victor still in the room? Yes.
Yeah.
So, Victor, we can go to the question of Marcio Pino. Marcio did the question, in the depth estimation phase, is the RMVS net a pre-trained, or you had to train it with your own data?
It's a pre-trained network.
Okay. I would like to know if any of you would like to make comments or say something about the work. Let's start by Vitor. Would like to make some final considerations.
I would like to thank everyone that seen the presentation and thank all the organization of the SVR.
Okay, thank you, Vitor. Gustavo, can you make any consideration? Your phone is mute. Your microphone is mute, Gustavo.
Sorry. I would like to thank you, all the organization of SVR and my colleagues of the lab have been working on. And it's just it. Thank you all.
Okay, thank you, Gustavo. Julia, you had the last three papers, so let me ask you something. Those papers are all related or are different researches?
No, these papers aren't exactly related, but at the same time they are because everything was to build this game at the end. But they are past works that I just organized and just sent. But some works I did 2 years ago, it wasn't anything, not all this year, but it's all related
Oh,
somehow.
okay, can make any final consideration?
Thank you very much for having me. Thanks for the opportunity and for everybody that watched.
So thank you all. I hope you have success in the continuation of your researches. So I would like uh, to tell the attendees of this section that the papers can be seen on IEEE, so the publication, and this video of this section will become available, will stay available on YouTube. And also would like to invite you to our invited speaker. The talk will start at 5. Help me, guys. Let me see, 5:50, I think. 5 15:30. 15:30, we have our invited speaker, Marcelo Wolff. He will speak about environments understanding for HoloLens. So he was in the development team of HoloLens. So I think will be a very nice talk. So don't miss this talk. So thank you very much. See you
Thank you.
in the
See you.
continuation of the conference. Thank you all authors.
Thank you.